Dear learners, welcome to the course Electromagnetic Fields. In this video, I will explain the capacitance of a coaxial cable. Already we have an idea about the capacitance. So here I am going to explain the two different methods to calculate capacitance of a coaxial cable. This figure illustrates the structure of coaxial cable. Consider a coaxial cable. Here, two cylindrical conductors are coaxially placed. That's why it is called as coaxial cable. Inner cylinder consists of radius A. The outer cylinder consists of inner radius B. The length of the cable is L meters. The inner conductor carries a charge density plus rho L coulomb per meter on its surface. Then equal and opposite charge density minus rho L coulomb per meter exists on the outer conductor. So now we are going to derive the capacitance of a coaxial cable in two different ways. One is Coulomb's law and another way from Laplace equation. First we are going to discuss about how to calculate the capacitance from Coulomb's law. So in this method, first we write the electric field intensity. So from Coulomb's law, we find electric field intensity for the corresponding configuration. So after that, we find potential difference with the help of the relation V is equal to minus line integral of minus to plus E vector dot dl vector. So from this relation, we find the potential difference. So this is the way to calculate potential. So in this case, we consider Q is equal to rho L into length. So assuming a cylindrical coordinate system, E vector will be radially outward from the inner conductor to the outer conductor. So this is the case for electric field intensity due to infinite line charge. So and this is for infinite line charge and it is given by E vector is equal to rho L by 2 pi epsilon R AR vector. So from this E vector, we have to calculate what is potential difference. So already we know that the potential difference is nothing but minus line integral of minus to plus E vector or dl vector. Here we substitute the value of E vector. We consider it is an infinite line charge. So minus line integral of R is equal to B to A rho L by 2 pi epsilon R AR vector dot dr AR vector. So we know how to write the differential length in cylindrical coordinate systems. It consists of the radial component only. So therefore the differential length, it should be along the R direction. So the equation number 2. Now this E vector is dot product with the differential length vector. This is the differential length along R direction. So after integrating with respect to R, we get this is the minus rho L by 2 pi epsilon ln A by B. So after calculating the value V, then we calculate capacitance with the formula C is equal to Q by V. So already we know that what is the charge. The charge is here we consider it is rho L divided by V. V is the potential difference. We substitute the expression for V. So now we take the ratio of Q by V. Rho L by 2 epsilon ln B by A. So rearrange this equation. We get C is equal to 2 pi epsilon L by ln B by A farads, where epsilon is the dielectric permittivity of the medium. Capacitance is generally calculated per unit length in the transmission line. So in the coaxial cable, capacitance per unit length is nothing but it can be written as C by L. Just we modify this expression as C by L is equal to 2 pi epsilon by ln B by A farads. So this is the method we calculate the capacitance. This is nothing but first we write what is electric field intensity for this configuration. From this we find what is the potential difference. After that we identify the type of charge distribution. Then we take the ratio Q by V. So we find capacitance of any structure. And another method is using Laplace equation. So here I am giving the statement of the problem. This is the statement of the problem. A cylindrical capacitor consists of an inner conductor of radius A and an outer conductor whose inner radius is B. The space between the conductors is filled with a dielectric of permittivity epsilon and the length of the capacitor is C. Find the value of capacitance using Laplace equation. Usually, in the statement itself, they mention Laplace equation. So, suppose if they ask in generally calculate the capacitance of coaxial cable, the previous method is very simple to calculate it. But here in this statement, they mention find the value of capacitance using Laplace equation. So, this is the structure. There are two cylindrical conductors which are coaxially placed. That's why it is called as a coaxial cable. Inner cylinder with the radius A and the outer cylinder with the radius B. And also one more information is given here for the inner cylinder the potential V is equal to V naught, as the outer cylinder that V is equal to 0. In this method, we have start the derivation from the Laplace equation. As we know that Laplace equation is del square V is equal to 0. This is the Laplace equation, del square V is equal to 0. Once we solve this equation, second order differential equation, we will get the solution for V. So after obtaining this V, so we find C is equal to Q by V. So after finding the potential V, we calculate the electric field intensity. From the electric field intensity, we find what is the flux density. From this, we find what is rho s, the surface charge density. And from this, we write capacitance equal to Q by V. This is the method using Laplace equation. So, it is very convenient to consider cylindrical coordinate system to solve this equation. As we know that the field lines are radially outward from inner conductor to the outer conductor. So, therefore, it consists of only the radial component 1 by r dou by dou r dou v by dou r is equal to 0. So, once we simplify this, we get dou by dou r. This equation, this equation dou by dou r dou v by dou r is equal to 0. Now we integrate this equation on both sides. We get r dou v by dou r is equal to integral 0 plus C1. We introduce the constant C1. So you very clear about this. Here the C1 is the arbitrary constant. It may be any variable. Here I am considering the constants as C1. And again we consist dou v by dou r is equal to C1 by r. Now we are going to obtain V by taking integration again. So now V is equal to integral of C1 by r plus C2 is equal to C1 ln r plus C2. In the equation 2, it consists of two unknown constants, arbitrary constants C1, C2. Generally, how we evaluate the arbitrary constants in second order differential equations? By applying boundary conditions, we can easily solve C1, C2. Now we are going to write the boundary conditions. These boundary conditions are mentioned in the statement of the problem. So V is equal to 0 at radius r is equal to V and V is equal to V naught at r is equal to A. So from equation 2 we can write two set of equations. So from the two set of equations we solve C1 and C2. Now C1 is equal to V naught by ln A by B. C2 is equal to minus V naught ln B by ln A by B. So now we substitute the expression C1 and C2. C1, C2 in this equation 2. We substitute in the equation 2, we will get here after substituting C1 and C2, we get equation 3. Then from V, we derived E vector. How we derive that E vector electric field intensity is nothing but the negative gradient of potential. That is E vector is equal to minus del V. Now we are going to take the gradient of potential minus dou V by dou R AR vector. Previously we have obtained the expression for potential V. Now we are going to differentiate this expression with respect to R. So now we get E vector is equal to minus V naught by R ln A by V AR vector volts per meter. As we know that the relation between D vector and E vector, D vector is equal to epsilon E vector. Previously we obtained the expression for E vector. Now we substitute it, we get the expression for this D vector. As per the boundary conditions between conductor and the dielectric, the D vector is always normal to the surface. Hence, dn vector. Rho s is equal to modulus of dn vector. So, this is the normal component, that is nothing but rho s exists on entire surface area of inner cylinder. So, Q is equal to rho s into surface area of inner cylinder, that is equal to V naught epsilon 2 pi L by ln D by A coulombs. So, it's now very easy to calculate. We obtained what is Q. Now we have the expression for Q, and then already we obtained V. From this we can find the capacitance. We just take the ratio of Q by V. We will get the capacitance. So now we can ensure the expression C is equal to 2 pi epsilon by ln D by A with the previous method. Both are same. Based on the statement of the problem, we can use any one method. But anyway, we get the same expression for the capacitance of a coaxial cable. C is equal to 2 pi epsilon by ln D by A farad per meter. The only difference is, for the first method in the Coulomb's law, we started from electric field intensity. After that, we find potential difference. From this, we calculate C is equal to Q by V. But here in the Laplace equation method, first we solve the equation del square V is equal to 0 depending upon the configuration. After solving this equation, we obtain the solution for V. So, from V potential difference, we calculate what is the electric field intensity and flux density. From this, we found what is the charge distribution Q. So, now capacitance is the ratio of charge to the potential difference. We find the capacitance using Laplace equation. So, in this way, we find the capacitance of coaxial cable using Laplace equation. I hope now you are very clear about how to calculate the capacitance of a coaxial cable in two different methods. Thank you.